This video is going to be all about integration. Integrals are used to find the area between a function and the x-axis. Finding an integral is the reverse of finding a derivative, so you can call integrals antiderivatives. For example, we know that the derivative of x squared is 2x, and if you don't know that, go ahead and watch my video on derivatives. Because 2x is the derivative of x squared, we know we can assume that x squared is the integral for 2x. Let's calculate an integral to find the area under a triangle. So here's our triangle. We want to find the area. Now the area of a triangle is 1/2 base times the height. So for our triangle here, we can fill in these values and we get 1/2 times the base, which is just x, times the height, 3x. That gives us x over 2 times 3x, which gives us 3x squared over 2. 3x was our function to integrate. 3x squared over 2 is the area of our triangle. This can be found using the power rule for integration, which we'll go over later. But which is basically the integral of some variable raised to a power integrated with respect to x is going to be equal to that variable with 1 added to the power over n plus 1 plus c, which is our constant for integration, which we'll also go over in just a second. So we found our area for the triangle by using the formula for the area of a triangle. Now let's try to find it through integration. So we're going to integrate 3x with respect to x. That's what dx is. Using the power rule, we'll get 3x to the first power plus 1 over 1 plus 1, and that gives us 3x squared over 2 plus c. So that checks out, but what's with this c? That's the constant of integration. It's for all the functions whose derivative is 3x. If you take the derivative of 3x squared over 2, you get just 3x. And it's the same even if you tack on, like, say you want to add 1. The derivative is still 3x because 1 is the constant. And when you take a derivative of a constant, it's just 0. We'll see the importance of including this constants later on. But for now, let's do some practical demonstrations. Let's say we have a tank filling with water. We need to integrate the flow rate in order to get the volume. So let's say our flow rate is constant and it's flowing at a rate of 1. So here are the graphs to illustrate that. We have our graph for flow rates and time. It's a constant rate at 1. And then we have our graph for volume over time. And that's going to give us a line whose equation is just x. That describes our increase in volume over time. This line also has a slope of 1. Now this is because the integral of 1 with respect to x, or in our case with respect to time, is going to be just x. Obviously plus c. The integral of any constant is just going to be x. As a side note, remember that the derivative of x with respect to x is just 1. So it makes sense that the integral of 1 is going to be x. So now we know all this. If our flow rate is 1 liter per second, we can deduce that after 1 second we have a volume of 1 liter. After 100 seconds we're going to have 100 liters, and so on. But what if our flow rate is increasing? What if it's not constant? So here are the graphs illustrating a non-constant flow rate. So our flow rate is 3x. That's the equation that describes it. In order to find the volume, we need to integrate 3x with respect to time, or x in our case. And just like before with the triangle, we're going to get a volume of 3x squared over 2 plus our constant of integration. And we see that plus c again. Maybe the tank had water in it before we started measuring the volume. The flow rate still increases volume by the same amount. So we see the constants can be important to remember. It could be a crucial detail. Let's look at some common functions and their integrals. The integral of a constant is just going to be that constant times x. Remember, we saw the integral of 1 was just x. That's 1 times x plus c. And if we remember the power rule from a previous video, we should know that the derivative of nx would be nx, and since x is to the first power, 1 minus 1, that's going to give us nx to the 0 power, which is n times 1, and that leaves us just with that constant n. Then we see the integral for a variable. Here we have the integral for x with respect to x. That's going to give us x squared over 2 plus c. Then we have the integral for x squared. That gives us x cubed over 3. And you kind of see a pattern here. When you're integrating, you want to add 1 to the power of the variable and then put that number below. That's the general premise of the power rule for integration, which we'll go into more in depth later on in the video. So go ahead and pause the video, look over this list of functions I made, because I guarantee you'll find some variations of these in your math classes at some point in time. So let's go over a few rules for integration. The first one being when you multiply by a constant. So here's the general form. We have a constant multiplied by our function to integrate with respect to x. When we have this, we can move the constant outside the integral and just integrate the function as usual. And then you're left with the constant times the integral of the function. I don't know, this is the integral. So if we were trying to integrate 3x squared with respect to x, basically we just have our integral. We can pull the 3 out in front, and we're just integrating 2x with respect to x. Then we can proceed with the power rule, which we're going to go over next. I keep bringing up power rule. I'm just so excited to get to it. So we get 3 times x cubed over 3. The 3's cancel, and we're left with x cubed plus c. So now finally let's look at the power rule. So if we're trying to integrate some variable x raised to some power n with respect to x, we're going to get x, then we're going to add 1 to the exponent, and then we're going to put that number in the denominator plus c. So if we have x to the 4th power and we're trying to integrate that with respect to x, we're going to get x to the 4th power plus 1 over 4 plus 1, which is going to be x to the 5th power over 5 plus c. And that's the power rule. Next is the sum or the difference rule. If you're integrating two functions that are being added or subtracted, we can separate those functions and integrate them and then add or subtract the results. For example, if we have 3x cubed plus x squared, and we're trying to integrate that with respect to x, we can rewrite this as the integral of 3x cubed plus the integral of x squared, both with respect to x. Don't forget that. Then we solve one integral, so we're going to pull our 3 outside of the integral. Then we're just doing x cubed with respect to x. That's going to give us 3 times x to the 4th over 4 plus the integral for x squared with respect to x. That's going to give us x cubed over 3 plus c. And that's how you use the sum rule. And it's the same for the difference rule. If this was a minus, this would just be a minus. Integration by parts is useful when you have two functions and they're multiplied together. So we have one function, that's u, and the other function, v. You can think of them as f of x and g of x, or whatever you want. And here's the general form for integrating by parts, where the u prime is the derivative of the u function, and then you have the integral for the v function there and there, and then you subtract. Let's do an example. So what's the integral of x times cosine of x with respect to x? We have x and cosine of x being multiplied, so integration by parts would be a good option to try and solve this. We'll call our x function u, and the cosine of x function will be our v. So first, let's differentiate our u function. So differentiating our u function, x, we get 1. That's our u prime. Now let's integrate our v function. And we know this from the list I showed you earlier. The integral of cosine of x with respect to x is just sine of x. So now we have our u value, we have our u prime value, and we have our integral of v with respect to x value. So now that we have everything, let's put it all together. So we can rewrite our original problem as our u, which is x, times the integral of v with respect to x, which is our sine of x, minus the integral of u prime, which is 1, times the integral of v dx, that's sine of x, dx. Now we need to integrate this, which is just sine of x because the 1 doesn't really matter. And again, if we look back at our common functions, we know that the integral of sine of x with respect to x is negative cosine x. So our final answer would be x times sine of x plus cosine of x plus c. And there we have it. We got that by integrating by parts. Let's go ahead and try this one. One last example. The integral of the natural log of x over x squared with respect to x. Again, let's set our u and our v values. Let's say our u is the natural log of x, and let's say our v value is 1 over x squared. The derivative of the natural log of x, which will be our u prime, is 1 over x. Then we have to integrate our v, 1 over x squared, which we can rewrite as x to the negative second power with respect to x. Now we can apply the power rule. So this gives us x negative 2 plus 1 over negative 2 plus 1. And this gives us negative 1 over x. Now when we combine, we get natural log of x times negative 1 over x minus the integral for 1 over x times negative 1 over x dx. All right, and then we can simplify this to negative natural log of x over x minus the integral of negative 1 over x squared dx. And then this gives us negative the natural log of x plus 1 over x plus c. So that's basically integration by parts. It can get a little messy, but it's a good tool for when you have two different functions you're trying to integrate, but they're being multiplied together. So now with that, let's get on to integration by substitution, otherwise known as u-Substitution. Integration by substitution, also known as u-Substitution, is a special method for certain integral setups. We need our integral in this form, where we have a g of x function inside of an f function, and then we have the derivative of that g function. Here's more of a clearer example. So we have our f function, that's our cosine function. We have our g function, that's x squared, and then the derivative of that g function, 2x. When we have it set up this way, we can use u-Substitution like this, where u is our g function and du is our derivative of that g function times dx. Then we would integrate the f of u function and then put the g function back in place of u. Let's do some examples. Let's do this one. So we'll set x squared to u, and then our 2x dx to du. Okay, now all we have to do is integrate cosine of u with respect to u. That looks a lot easier. We know that the integral for cosine of some variable is going to give us sine of that variable, u, plus c. Now let's replace the u with what it originally was, x2, and we get sine of x squared plus c. Great, and that's our answer. We used u-Substitution to do that. This was kind of an ideal situation though, because we already had our derivative of the g function in the problem. But what if we don't get so lucky? Let's do one that's a little bit less ideal than the previous one. What if we have cosine of x squared times 10x with respect to x? Looks a little different, but not really. But let's go ahead and solve it so you can kind of see how we can manipulate these problems to kind of fix it so that we can work with them easier. So we know we need a 2x here for it to work. So let's make this a 2x. Let's pull a 5 out in front of the integral. Now it looks like the previous integral. Actually, it's exactly the same. Our final answer will just have a 5 in front of it. So this one wasn't quite ideal, but it really wasn't that bad. Let's do one more just to drive it home. So looking at this, we can see that the derivative of x squared plus 1 is going to be just 2x. So we want to make this a 2x. Let's do a little bit of manipulation. So what we can do is we can put a 1/2 in front of our integral and then put a 2 in front of the x in the numerator. Then we have our denominator down here. And this is totally fine because the 1/2 and the 2 cancel each other, so this is allowed. Let's go ahead and make x squared plus 1 our u, and then the 2x dx will be our du. So now we have 1/2 the integral of 1 over u with respect to u. Much simpler. We just need to remember the reciprocal rule for integration that was in the list I showed you earlier. So this is going to give us 1/2, and then the integral for 1 over some variable is going to be the natural log of that variable plus c. Now all we got to do is replace the u with what it originally was, and this gives us 1/2 times the natural log of x squared plus 1 plus our constant of integration. Great, that's not too bad. Of course, these can get much more complicated. I encourage you to keep practicing and do some practice problems. That's it for this video. I hope it helped. Thanks for watching.